All right, first things first. Do you recognize, is it yours? Don't recognize, it's not yours yet, okay. So let's switch gears, and the first lecture this afternoon is going to be given by Marta Constantinou from Temple University, who is starting her set of lectures about lattice QCD.
Thank you, Alexei. Thank you for inviting me here. I am kind of a Trojan horse because I am in a different topical collaboration than SURGE. I'm in QGT topical collaboration. I will talk a bit about it in the next lecture. So I don't belong to SURGE, but I know very well how these things go. And I do recognize not everybody here is a lattice practitioner. So let's get to know each other. So I can maybe customize my next lecture based on your background. So how many of you have written codes, analysis codes, whether it's Python, C++, or another language, which was more than 500 lines long? Okay, very good. And how many of you have you been staring at data, whether it's from experiments or analysis of Monte Carlo at 3 a.m. wondering what the hell this is going to be? Okay. And now, very importantly, how many of you have blamed systematic uncertainties for your bugs? Okay, I am guilty for all of these things. But very importantly, and this will guide my lectures, how many of you believe that we will reach a point that we will solve analytically four-dimensional QCD? Okay, so very, very brave people. Well, I would say that we cannot, at least for now. I don't know, 100 years, people will say, oh, these people didn't know what they're doing. But lattice QCD is the way to go to solve theoretically and encompass all the non-perturbative aspects of QCD from first principle. I have been doing this for a long time. It's equally beautiful and frustrating. I am not going to lie to you. Also, something that I have noticed compared to the previous lectures, and I guess many of the lectures you will see, is that I will keep the conversation a bit more descriptive. There are no analytical calculations I can guide you through. We do not solve integral analytically or in Mathematica and so on. So we use supercomputers, and I cannot bring one here and show you what we do. So I will try and get things going. And my goal is for those who are not lattice practitioners to be able to follow lattice talks, be able to evaluate what the systematic uncertainties are, and just be a good judge of what lattice practitioners are doing. So that is my plan. I will keep some things descriptive, only give details when it's necessary. I will focus on lattice QCD, but the field is much more wider. There is the lattice gauge theories that incorporate physical and unphysical theories. So this is a tool that basically you can discretize different theories of your choice. So you can take a totally unphysical theory and just try and do numerical calculations as if what would that theory predict, for instance. But I am focusing on lattice QCD. So we are only talking about describing a nature to the best of our abilities. And this is something that is going on for a few decades now. In the 80s is when the first ever calculation appeared in lattice QCD. It was something that today is very, very trivial, but the field has advanced. It addresses a lot of physical questions, and it complements the experimental program. of both hot and cold QCD, from nuclear astrophysics, hadron structure, nuclear structure, fundamental symmetry, spectroscopy, and all of these things are to complement the experimental program in the US. Since we're talking about EIC, and my field of research is hadron structure, this is what I will focus on. Last year, there have been a talk given by somebody who is in spectroscopy. So their talk is more geared towards spectroscopy. You can look at previous iterations to see also progress in various fields. My plan for today is basically give you some general aspects of lattice QCD and what the formulation is about, and how do we practically try to extract physical information? What are the steps that we are doing? I am not sure about the structure of Thursday yet. I do have an idea. What I want to talk to is hadron structure from lattice QCD related to EIC physics. But there are a lot of novel methods that go beyond traditional hadron structure. Maybe some of you know that there has been a lot of effort to calculate X-dependent distributions from lattice QCD. That was considered a dream a decade ago, and people thought this is a high-risk, high-reward science. But we are there. We are doing a lot of calculations related to PDF, GPDs, and TMDs. I know Yoshitaka has talked about some aspect earlier. So just maybe you could tell me what you would like to hear, and if it's something that falls under my research, and I can maybe include something for that. But as I said, I'm a Trojan horse, so I am going to talk about synergistic efforts, and in particular, what we do within our topical collaboration, the quark-gluon tomography collaboration. I have a few resources. You can, if you want to read more, this is more of a rigorous reading material. They're books. They're very well known for Latin practitioners, and many people have been educated and trained using these books. But I would not suggest that people who are outside the field dive into these books. They get very technical very quickly. I would encourage you to see a couple of review papers. So recently we celebrated 50 years of quantum chromodynamics. We were invited to write a review article, and it has not only important things about QCD, about lattice QCD, but also QCD itself. So it's a very interesting read. It has been written also besides people who are currently doing research and very active in QCD, there's also people who have been there at the beginning of the field, or almost at the beginning of the field. So I do encourage you to read that. I have a QR code, and we have written a component which is particularly on lattice QCD. Hadron structure is down here, but there is a lot of useful information. So if you are working in lattice QCD, or if you know that you collaborate closely with lattice QCD practitioners, I would say take a look at this section. Since we are interested about EIC physics, let me also mention the yellow report that is already 3 years old. It's a huge effort. I think it's more than 140 institutions that have participated in this write-up. We have a section which is connection with other fields and theory, and how the EIC science is relevant for what we do. You can look at section 7 is where we have some connection with lattice QCD. So what I view lattice QCD as when it comes to EIC science is a window into the non-perturbative dynamics of the hadron structure and interaction. So you can look at this if you like. The QR codes I included are for the free to access PDF files. Okay, let's talk a bit more specifically for today's lecture. I will briefly talk about how lattice QCD was formulated, what is the idea behind it, which is basically the basic steps and the logic why this works or should work. And then I will talk about a bit about the landscape of the numerical simulations and set the stage for the next lecture, where we're going to dive into physical quantities and talk about what kind of things, what are these data that we calculate look like, at least for hadron structure. So that's the plan for today, and hopefully I will get to that on time. So why should we incorporate lattice QCD? Why do I say that it is essential to complement the experimental and theoretical program? To answer this, we have to look at the formulation of QCD Lagrangian. We know QCD is a non-abelian theory. It has a symmetry group SU3, and this is very complicated. It's much more complicated than QED, for instance. I have here the QCD Lagrangian density that incorporates the quark component, the quark fields are these psi that I'm sure everybody has seen. F mu nu is the field tensor that contains the gluon fields. So this is the fermionic component. It contains a kinetic quark energy, the mass terms, as well as quark gluon terms into this D. But also the complexity comes in addition to, because we have interaction between gluons. Unlike QED, we know QED is easier. The photons don't interact with photons, but here we have to deal with that. And that's the nature of QCD that makes it very, very complicated to solve and cannot be solved analytically. So when I want to motivate QCD, I always like to go, lattice QCD, another way to look at this is through the coupling constant of the strong force. We know how this is not a constant, but it varies with the energy scale. We know this from experiments. We know this from theory. This is we have concrete evidence. And many of you are working in a region where perturbative tools are successful. So when we are analyzing cross-sections from experimental processes, why are we allowed to separate the perturbative component and the non-perturbative component? How can we get information on the hadron structure? That is because we utilize asymptotic freedom of QCD. At very, very high energies, you can treat the components that are process specific, you can treat them perturbatively, and this kind of factorizes your cross-section into a kernel that is perturbative, and then is the non-perturbative component where you can get physics out of. We do not have anything like that on the lattice. On the lattice, we can simulate directly the non-perturbative component, but we can compare with experimental data by utilizing asymptotic freedom and knowing that the non-perturbative component is process independent. I think I will talk about this next time, just a bit of a motivation here. So you see how at what energy scale we are referring to. However, if you go at very low energies, this is the coupling constant becomes very high, and high enough that we can no longer use perturbative tools. Perturbation theory fails to converge, and therefore you cannot use that because the next to leading order is more important than the next to leading order, and so on. So every other order is more important than the previous one. There is no convergence, and that was kind of a worry at the early stages that QCD should be abandoned because it doesn't make any sense. I cannot solve it until other non-perturbative formulations. And we know that, for instance, at that level, we have quark confinement, and we cannot observe free quarks in in nature, and this is the particle jets that are also an evidence of quark confinement, that you have the hadronization of quarks and gluons where new hadrons appear and they form these jets of particles. Okay, so trying to explain why do we need to do lattice QCD, I use this analogy. Some of you might have heard me talking about it. I know Alexei have seen this before, but in my opinion, it's the best way to explain why we need that. And I go back to my Greek heritage, and I come across the Gordian knot that some of you may know. If you don't, it's basically a very complicated knot. It's shown here. And it was so complicated and so there are so many knots that it couldn't be unsolved. And many people have tried to solve it. It was kind of a spectacle. People were going into stadiums, watching other people trying to solve the knot. I do not know what was happening to people who failed. I don't know if they were fed to the lions, but the story doesn't include any such information. But what was the outcome of this? Every time somebody was trying to untie the knot, they couldn't, and it was a total fail. And then they invited Alexander the Great. He was recognized as a great mind and was asked to untie the knot. So he went to the stadium. He spent quite some time studying the knot and how it can be entangled, but eventually he took out his sword and he cut the knot, and he said, "Odi deline de covete," and that's for cut whatever you cannot untie. So that's something that reminds me of why we do what we do with the QCD Lagrangian, which is very simple. You can put it on a t-shirt, on a mug, but we do know that this is very complicated. There is a hot QCD vacuum. To my undergraduate students, I tell them this is like a pot of boiling water, and you want to do experiments by throwing pasta, and then good luck figuring out how to predict the motion when there is such a hot background where you have to do the experiments. So because we cannot solve this analytically in a similar fashion as Alexander the Great, we just discretize space and we simulate whatever we cannot solve analytically. That's my naive interpretation of what we do in lattice QCD. And of course, this is very complicated theory. We use supercomputers to do our calculations, and you can solve QCD, but also other kind of theories. All right, so how was lattice QCD formulated? I will get a bit technical, not too much for your taste, I hope, but it relies on the path integral formalism. We know classical particles behavior. You have a unique trajectory. If you want to identify the trajectory of a motion of a particle going from A to B, there is one unique trajectory governed by the theory, basically. If I drop something from a given height, I do not have many possibilities. Assuming this is a controlled environment, there is no wind and so on. Everything is done in vacuum, at least in classical vacuum. And I know what is going to happen. The theory predicts a unique trajectory. And other classical systems have the same behavior. But if you look at quantum particles, then you know that there is no unique trajectory. You have a lot of possible trajectories weighted by the theory you're studying. And basically, if you want to take a propagator, as we know in quantum mechanics, in the path integral language, you sum over all the paths, but these are weighted by the action of your theory. And that's a starting point for lattice QCD. This is equivalent to Schrödinger formalism, but it's more intuitive interpretation. It's practical for quantum mechanics because we can incorporate all these paths weighted. But if you want to study quantum field theories, then this is extremely valuable and important, and it's successfully applied to lattice QCD. We know that we also have to, for solving QCD on a lattice, we have to go through quantum field theories. You do not have a given number of degrees of freedom. You have infinite degrees of freedom. You have quarks and gluons arising from the vacuum besides the valence sector. So considering that we are not working with a finite degrees of freedom, using even Schrödinger's equation, it's extremely difficult, I would say, nicely. It's basically impossible. So quantum field theories is what lattice QCD relies on. So our degrees of freedom is quarks and gluons, and these are interpreted as fields. We go through the path integral formalism. So any quantity or any measurable quantity we want to study has to go through the partition function of QCD. You see the QCD action here. And the observables are basically vacuum expectation values of operators that contain the partition function, but also weighted by the action. So similar to what you would see in quantum mechanics. So here is a problem, though. The problem we have is that this exponential is complex, and therefore this makes your integral not converge, kind of fluctuates and not converging, so it oscillates, doesn't give you a finite number. So with this formulation, it's not sufficient to be able to calculate anything physical because I have a problem of the so-called sign problem or the imaginary phase problem and so on. So we need to deal with that if we are able to ever calculate this kind of measurable quantities. And there is a simple idea that it took a long time to be able to make sure we understand, we get concrete physics out of it. And that is to remind that inside this action, you have an integral over time. What if you take your time and you rotate it to some other imaginary time? You call this Euclidean time. And the role of this I multiplied by the external one is to make this exponential now having a decay behavior. It's no longer oscillatory. And we can use something like statistical mechanics methods now, where we can treat this as if it's a Boltzmann probability. So this means that I can try and solve QCD through this path integral formulation not in Minkowski space, but in Euclidean space. So if you're a theorist doing analytical work, I bet you'd never need to rotate in Euclidean space. You work in Minkowski metrics, and you have certain rules for your matrices and everything. But we always have to take what you give us. Whatever Yoshitaka has shown you earlier, he has shown some equations with operators and decompositions and how can you relate a matrix element into physical quantities. We have to rotate all of them in Euclidean space. That's not a problem for what we want to do, but it is certainly problematic if you want to study time-dependent phenomena. So if you want to study the time evolution of the universe, classical computers, because of the oscillatory phase issue, cannot be used. But you can study thermalized phenomena where the time evolution doesn't matter. And there is all the science I talked earlier about hadron structure and spectroscopy. These are not timed evolved investigation. So we can very well use lattice QCD for that. So what I described so far has nothing to do with lattice. The word lattice is introduced because we need to recognize that even though we have a very good methodology to utilize statistical mechanics for QCD, now I have to solve the integrals. And I have infinite numbers of degrees of freedom. So how am I going to do that? We cannot do this analytically. You have to simulate it. And if you're going to simulate something, you need to put it on a computer. We know the integrals become sums. They have finite limits. So basically, you're introducing a space-time discretization. And that's where lattice QCD comes in. It's at that stage where we have to take the Euclidean time. Even if you're in continuous space, theoretically, this is well defined. However, if you want to actually do calculations, the only way to do that is in a discretized space-time. But remember that time, we treat time as a fourth dimension that doesn't have more significance. It doesn't have a time significance. Okay, so a couple of more theoretical aspects about the lattice formulation that was developed by Kenneth Wilson. Initially, he was not thinking about QCD. He was thinking about condensed matter and how to renormalize and regularize theories to all orders. And his ideas were applicable for QCD. And that's how lattice QCD was born. He got, well recognized for his achievements. And the first calculation was done in the 80s by Michael Kreutz. I mean, I do encourage you to go and look at it because it seems so funny now to read in abstracts in the 80s. We perform a state-of-the-art calculation of 4 by 4 by 4 by 8 simulations, when now we do 128 cubed times also for the time component. So what they consider pioneering calculations were, we don't even give them to our high school students nowadays to do. So the field has progressed a lot in the last 40 years. And basically, the idea remains the same, and it's simple enough to be described without too many equations. What is done is basically the fact that you discretize space-time. You have now introduced a UV cutoff because your integrals become not infinite, but they're cut by pi over a. And a is a discretization, is the nearest neighbor, is the distance of the nearest neighbors. That's one thing that you need to impose on the lattice. You need to decide what is the distance between the nearest neighbors. That's what we call lattice spacing. Always we indicate it as a. But also the fact that your integrals become sums of discrete components. This has an infrared cutoff and makes your degrees of freedom finite. And I will come back to that in a moment. So that's the two important elements, is the UV and IR regulations by making the integrals finite, but also simulate them in a finite space by discretizing space-time. And eventually, it has been shown very concretely, and I want to emphasize this. Lattice QCD might have been hand-waving 40 years ago. Today, we are able to make predictions for some aspects of nature. We are not doing a good job for everything. We have a lot of systematic uncertainty. We have a lot of things to control. But there are things we have very good confidence about. And one of the reasons is that theoretically it has been proven. You can, if you study the discretization equations, you will see that if you take the space to be infinite, so lambda go this L, which is the length of each direction, if you take that to be infinite, but if you take also the distance between the nearest neighbor to be 0, you recover continuum space and you recover the continuum equations of QCD. So you get the QCD Lagrangian as a theorist would. So as long as we're working with finite A and L, we have some cutoff effects, but this can go away by taking this regulator to the right limit. I will come back to that, how do we do that practically. And of course, I should have already said that this is a first principle calculation in the sense that you do not modify the equations of the theory. You just discretize them and put them in a box. Other than that, you do not truncate, you do not make approximations. You don't say, oh, this might be small and I can ignore it. Nothing of this happens. It's a truly non-perturbative approach. I should say, though, that we have limitations. When I showed you the coupling constant, and I talked about what are the energy scales, I have talked about lattice QCD being at the non-perturbative component. The fact that the inverse lattice spacing becomes a limitation of what can we do. So we cannot do very, very high energies. It's cut by what is the inverse lattice spacing in GeV. Typically, nowadays we have maybe up to 4 GeV as a lattice spacing. But if you want to study hadrons, the hadronic energy level is much lower than that. So you can study hadrons. If I want to study GPDs that you learned in the previous lecture, where you have momenta, when you do the lattice calculation, you have to remember that I cannot infinitely use any momentum I want, and so on. So there are a lot of limitations, but there is a sweet spot where lattice QCD can really be important. Okay, so we discretize space-time, and now I have to do this I define what the lattice spacing is going to be, what the lattice size is going to be. You decide how many points you're going to simulate and how what is the step you're going to put between space-time. But the other thing that enters the theory are the quark masses. Somebody's taking over my... Okay, I thought you were taking over my slides. So quark masses is the other thing that appears in the QCD Lagrangian, and we need to fix it. So we choose what that can be. I can do simulations where I say the quark masses are such that they produce a proton which is twice as large as it is in nature. Usually we look at the quark mass value with relation to the pion mass, and 10 years ago, it was really, really pioneering to be near the physical pion mass. So basically what this means is that you give some values to your quark masses, and when you go to calculate the pion mass, you produce something. I will explain later today what this means, but I can find it to be, if I want to simulate nature, I should choose such values for the quark mass that reproduce the right spectrum in the right values. 20 years ago, they were considering pioneering to do simulations at maybe 500 MeV pion. So the physical value is about 140 rounded. So instead of simulating nature, you pretend that you live in a world where your pions are 4 times larger than that. So This is what was considered pioneering. I'm not going to talk about this extensively here, but the reason why we were forced to do that is because numerically you have to do inversions of a lot of matrices, and those matrices incorporate the quark masses. If the quark masses are very, very small, the convergence of the inversion is very, very slow. So it might take years to be able to do a calculation. So with the computer power available 20 years ago, they could reach as low as 600 MeV pions. If you go even beyond that, maybe, I mean, I have seen papers in the early 2000s saying pioneering calculations of 700 MeV and between 700 and 120 MeV. So all of these things have advanced. We are now able to simulate nature, so we can program quark masses as encountered physically to reproduce basically the energy spectrum of the hadrons correctly. And of course, it goes without saying that you don't want the step between discretization to be very large. You want it to be very, very fine. So you don't want to miss anything happening in here. So if I take this space and I cut it into 2 pieces, I suddenly group all of you into pieces. And I kind of miss what's happening in between. The more more fine my discretization is, the more I can study this phenomenon. That's one thing. And the other important thing is that the lattice, I want it to be large enough. If I want to study the behavior and interaction of this classroom, I cannot take, I cannot create a box around, I don't know, these Eurocomputers. I need to have a big enough box to capture the interaction and the phenomenon I want to study. Discretization is not unique. You can be introducing this lattice spacing and making your QCD Lagrangian on a discretized space can be done in many different ways. I like to explain this as if, let's say, you want to discretize a derivative. You learn that the naive discretization is take f of x plus dx minus f of x divided by dx. It's the naive discretization of a derivative, right? But then you can define a derivative that has better limit, faster limit, where it incorporates 3 neighbors, not only 2. Or you take x plus dx and x minus dx, and all of these have different properties, right? So think about the lattice discretization in a similar way, that there is no unique way to discretize space-time. There have been a group of discretizations that classify under different names. I will come back to that in a moment, but all of them recover the continuum limit and can be used for lattice simulations. I did mention earlier that we are using statistical mechanics methods. I just noticed I'm running out of time, so we'll try and go a bit faster. We have, basically, we use Monte Carlo to simulate nature. This gives a stochastic estimation of the path integral. And I also want to emphasize that a modest lattice size nowadays is 48 cubed in the spatial directions, 96 in the temporal directions. If you multiply these, you create a grid of 340 million degrees of freedom. So you have to simulate this. That's why we need supercomputers. These cannot be done on a small cluster even, not talk about our personal computers. So because we're using statistical mechanics, we have to keep in mind that we have this Boltzmann probability. So we need to have basically QCD Lagrangian is always there to tell us what is the acceptance probability of a path, and we incorporate that. We calculate expectation values of operators, as I said earlier, and because the background QCD Lagrangian is extremely complicated, what we do is basically we take pictures of QCD background, and for every static picture I'm taking, I repeat a measurement. I do a calculation for that snapshot. So we need to do this for many, many times. In the end of the day, we collect millions of data and million statistics. And one of the reasons why we need to go so high is because there is correlation and local effects from the QCD vacuum and gauge noise. So it smoothens out these local effects. Where do you have glucose affecting your proton energy, for instance, and so on. So that's why we need to repeat this n times. If you're doing a classical experiment, I know that all of you have done an experiment of, I don't know, free fall. You put things in a vacuum, you do it 10 times, you're good to go, that's it. It's not going to work here. There are a lot of fluctuations, and to be able to smoothen out and remove local effects, we need to do this a million times sometimes. So we take average of the results, we do statistical analysis methods, and so on. I think I'm gonna skip this. It's a boring stuff. It's basically, I only want you to know that the quark fields are simulated on the lattice points. In between them, we define the gauge links. We need to create gauge invariant quantities, and that is products of psi bar, and gauge links to connect them, or closed gluonic loops. So we have to, when we formulate our discretization, it has to be done with respecting gauge invariance. If you don't do that, it is possible, but it's just a headache to do a lattice calculation. You have to make corrections after corrections. So better deal with terms that are only made from gauge invariant components. Psi bar, gauge link psi, or gluon loops, closed gluon loops. Of course, the easiest one is a square, but you can have different shapes. This is relevant. I have some backup slides, and this is relevant when we discretize our action. That's why this is important. There are a lot of issues that we have to go around, but my message is that there is no free lunch. That's what the no-go theorem says, that you cannot have, basically, the proof is that they have proven that you cannot design a lattice formulation, a lattice discretization that has perfect symmetries and all the properties of continuous QCD. You need to give up something. Maybe you have something that respects chiral symmetry. It's going to have some other effect. I am personally working with twisted mass fermions. They have automatic improvements, but you have to give up chiral symmetry and so on. That is why there are a lot of groups working with different formulations for hadron structure spectroscopy and other investigations. And all of them have different systematic uncertainties. In the end of the day, if all of us do our calculations correctly, estimate our statistical and systematic uncertainties, take the continuum limit, we should be able to all get the same results, continuum QCD. So for some quantities, such as the axial charge, this was done, but not for everything that we have available. Let me skip this, even though it's interesting. But this is basically a landscape for hadron structure. What kind of, these dots are basically different ensembles, different lattice formulation and discretizations. We call them ensembles, coming from different collaborations And different collaborations use different actions. So ETMC uses twisted mass fermions. This is where I belong in this collaboration, but other use different formulations, whether it's Wilson, Clover. So when you hear this terminology, it's basically different discretizations. What is important to emphasize is that this line here, so this is a plot showing what is the pion mass that this ensemble corresponds to. We know the physical value in nature is this black line, but you see some are 300 MeV. If I was giving this lecture 20 years ago, I would go above 1 GeV to tell you what is modern nowadays. And the other component which is important is not only what are the quark masses, but what is your discretization? All of them, okay, not all of them, but most of them are below 0.1 Fermi. And that's very important because, as I said, if you want to study something, you need to, the discretization cannot be too sparse. That is because you lose the physics in between. So when you see these white squares, you cannot capture what's happening inside the whites. It's basically empty space for you. You don't see that. So the more dense it is, the better you can capture the quantity of interest. Do you have any questions?
I have one question about one of the earlier slides. Why have a different number of lattice points in the time direction with respect to?
Okay, that's I will show you just now.
Okay.
Hold your question for a second. I will show you on a plot. Okay, so what should we study? What are we doing basically? We're doing Monte Carlo, we produce these snapshots of QCD, and we want to use these snapshots as our background to do the calculation. What are we doing? We need to find something easy. The easiest thing to do is calculate some hadron masses. I am not talking about modern spectroscopy. Modern spectroscopy is doing miracles and predicting states and excited states and exotic states, and has gone beyond anything I'm going to show you. But let's say I want to calculate what is the mass of the pion, what is the mass of the proton, the kaon, the rho meson, and so on. That is relatively easy because this relies on the propagator. So we have to remember that because mesons and baryon have different quark content, quark, anti-quark, and 3 quarks here, we depict our calculations differently. This is just a schematic way to show you this. This has nothing to do with the diagrams that you may see in perturbative QCD. This is for lattice practitioners to show you, I am now calculating a pion, a meson, or a baryon. Yes?
So you're calculating masses, but a few slides ago, masses were part of like the parameters that you put into the lattice.
Yes, so the quark, I'm not calculating quark masses. I am calculating physical hadron masses. So basically, now there is a lot of expertise. So people, they kind of know what input to give, to know what output, but let's say you have no idea. You give a value for the quark mass, you do the simulation, and you want to see how close are you in nature, calculate what I'm going to show you now, see what the pion mass is. Is it 140 MeV? If it's more, you have to go back and retune. So this is something that is done with people who are doing the configuration production. There is a tuning phase that there is a lot of expertise, so they don't shoot in the blank, but basically they know approximately where they want to be, and they know approximately what the parameters should be, and then they go back and refine it. So it's a process of tuning. That's how we call this. Okay, so there is a long theory behind all these things, but we have basically, we use interpolating. We don't do anything experimentally. You basically do everything on a piece of paper. You say, let's say I want to work with a meson. I write down on a piece of paper an interpolating field that corresponds to, has the quantum numbers of a pion. And I also have another final state for the pion here. And I do weak contractions to create propagators. So I need to contract quark and anti-quark to create a propagator. And I assume you have seen this in quantum field theory, where you do the weak contractions and you take different combinations and all of them, and the signs when you commute quark and anti-quark and things like that. So all of these things is done on a piece of paper. And then once you have that, you go and code it. And everything is done in terms of propagators. And this now uses information from QCD, and that's a very costly part of the calculation. If you want to see how this is defined, it has inversions of matrices. So this becomes extremely complicated. But setting up the computational component, it requires that you do an exercise on a piece of paper where you do all your contractions between the quarks of the external state, you just propagate them. Now, if you have you have a positive pion, you know it has an up quark and a down anti-quark. So you have here you have for the interpolating field the two cases, and then you have to contract them. The up quark will contract with the up anti-quark, and so on. So there are all of these things that you have to take into account. If you're dealing with a proton where you have two up quarks and one down, then you have more combinations and your mathematical analysis becomes a bit more complicated. You have more terms to write on a piece of paper and then go and put it on a computer in terms of a propagator. I don't want to take too long to talk about this because it's beyond my talk. You can study it later and ask me questions if you want. But basically, it can be proven if you take the Heisenberg picture at the hadron level for the 2-point function. You can see that basically you have, if you calculate this 2-point function that incorporates the propagator, it includes information on the hadron mass. That is why I said you simulate some values for the quark mass, and now you go and test. If I calculate the 2-point function, which is the figure I showed you, this artistic interpretation I showed you previously, which is basically hadron-hadron sandwich between hadron, bra, and ket, you will see through the slides I skipped that it contains basically the masses of the hadron of interest. So you can calculate this on the lattice and relate it to this quantity. And I go back to your question. You said, why do you do the time component more? Depending on the investigation. So if you want to study spectroscopy, it's convenient for them to use different lattice spacing in the temporal direction. So they make them more dense in time components. But for hadron structure, there is no such thing. We deal only with symmetric lattices, so that the discretization in space and time are all the same. But here is why it's important to have many of them, because even though the T doesn't have the time interpretation, it still appears in a special location compared to the spatial directions. It appears in two exponentials, the same way if you are going to write a wave function is you can get any state right in terms of eigenstates, and all of them have a coefficient and they have an exponential with the energy of the state and time, right? even though now I'm working with a Euclidean time, I'm not messing up the equations. So this exponential still appears, and having a longer time frame, it allows me to study more, for instance, the time dependence, not the time, but the mass dependence as a function of time. That is why we have this longer, because we use this to identify ground state. And you want to have many, many points to be able to do so.
I follow.
Yep.
Is it better to have a different number of lattice points or a different lattice spacing?
Definitely have different number of lattice points. If you want to introduce anisotropic lattices, it becomes a real headache for hadron structure. It's better if you keep your discretization the same for all directions, because you don't need time for anything other than recognizing it appears in these exponentials. And if you allow time to go long enough, the exponential decays fast, right? So if you have a sum, if you have a sum of many states, this is, let's say, quantum mechanics. A state can be written in terms of eigenstates with the eigenvalues that are the energies. You have this sum over all the eigenstates. Each one comes with a different exponential. The eigenstates that have a large value for the eigenvalue, a large value of energy, those will decay very fast. E to the minus 5t decays faster than e to the minus 1t. And that's exactly why we need time to be able to run, so we can explore how much time should I allow for this quantity that is a sum of all the states, ground state and excited states. How much time should I allow for eventually from all of these terms to have the leading one participating? And how do you know you have the leading one? You find here a plateau. And you don't know where you're going to find the plateau, and you don't want to keep your time direction very short. Otherwise, you will run out of possibilities. So that is for one particle. People can do a state. Basically, you can wait long enough to see a plateau, and then you fit. More modern analysis methods, they say, wait a minute, since I know that there are the first 2-3 excited states, can I incorporate them in my data and do a fit which is, I don't know, 4 or 5 parameter fits? This becomes more complicated. It's not uncommon for people to allow time to pass, find the plateau, instead of doing a 2-state fit or a 3-state fit. But all of them should converge to the same number. You see here that the two fits eventually they have to agree if you want to claim you found your ground state. Okay. And okay, I don't want to talk more about spectroscopy. For me, the interesting part is basically a hadron structure. Very, very quickly, I want to say that what is the difference in what I have shown you previously with what we are going to do in hadron structure? Well, you need that component. You need to know the energy of the particle. You calculate basically the 2-point function that gives you the energy, and it's basically the Bragg of the hadron states. But you learned in the previous lecture about operators and physical quantities and observables. How do we calculate the orbital angular momentum, the spin, the momentum fraction of all of these, the proton, for instance? We need to calculate 3-point functions, which is basically terminology to say that you no longer have a propagating hadron, you have a hadron that interacts with something. You probe the properties of your hadron with some operator, which resembles an interaction. The same way you have a lepton to hadron scattering, right? You need your probe to see the structure of the hadron. This probe for us is an operator. Yes.
I was wondering why these diagrams, it kind of seems like space and time are propagating from right to left instead of left to right. Is there a significance behind that?
No, just historical reason you can mirror it. There is no reason why. You're right, it's counterintuitive because you would expect to go from the other way. There is no reason for that. Just mirror it, it will be the same thing. Okay, so this operator that I inserted, which I have written in a very simplistic form, it might probe the quark content of the hadron or the gluon content of the hadron. Depending on what it probes, you have to go back and do the weak contraction. A proton only has the interpolating field of a proton, a pion, and kaon has only quark and anti-quark. So if you're going to contract those two without an operator, it's a simple, you create propagators of quarks. If you're going to insert an operator, you learned about gluon GPDs, for instance. You need a gluon probe. And that means you have something that resembles like this. The quarks will have no option but to contract with each other. The external quarks, the quarks of the external states, they will contract with each other, and the gluon fields will create these gluon propagators. If you want to probe quarks, then you put a quark operator here, and the weak contractions have many options. You can either take the quark and anti-quark of the operator and contract it with each other, and therefore the quarks and anti-quarks of the external state, they contract with each other, and you create what we call disconnected. It's not disconnected. I know that some of you are working with diagrams that you amputate, and you want them to be, you want to get rid of amputated, you want non-amputated diagrams. This has nothing to do. There are gluons connecting all components. We just don't draw them because it's non-perturbative. I cannot set a certain number of gluons. You have infinite numbers. So these are not to be amputated. There are connections between them. And the other more easy option, easy computationally, is the fact that the quark and anti-quark of the operator are contracted with the quark and anti-quark of the external states, and that is what we call connected. Basically, this operator here connects to the external states. Here, the disconnected is the quark and anti-quark of the operator. They contract with each other, but still, there are terms that connect the two via gluons. And it's extremely complicated. If you want to study EIC, EIC is focused on the C quark, and naively speaking, to first order approximation, this is coming from the disconnected contributions. A lot of theory that I don't want to go through, but a couple of minutes to say that there are a lot of uncertainties in lattice calculations. The signal decays by doing different things like adding boosted hadrons or decreasing the quark masses. Your inversions become very, very slower, and then you have a signal problem. Also, but besides the signal and the statistical error, we have to worry about systematic uncertainties. Remember, we discretize space. So how big is your discretization? How big is your volume? Taking the ground state and isolating from the exponential, and many, many more are extremely important. So there are a number of ways to do that. You can basically calculate multiple ensembles to find different systematic and eliminate them and so on. So that's what I have for today. I ran a bit over time. But basically, I hope it's clear to everybody that we cannot solve, at least for now, QCD Lagrangian can be solved numerically. Lattice QCD is not a model, but it is a non-perturbative approach for capturing all the QCD non-perturbative dynamics. And there are a lot of challenges, but a lot also of advantages. So since I have your attention and I'm not going to be here for long, and maybe you have some questions for me, let me bring to your attention something that will be very relevant for this audience. We are organizing a conference, the EINN in Cyprus, where I come from actually. But that's not for me to advertise the conference. I want to advertise the workshop. The Frontier Career Workshop is organized by postdocs and students, and it's a career workshop. So they invited people from industry and academia to talk about career advice and also give some introductory lectures. There's opportunity for students to give some small presentations during that 2 days, but many of them continue to the main conference. There are poster sessions, and I have been attending this for many years now, and I have seen many students and postdocs benefiting by the interactions from this. I am not an organizer of the career one because this is for students and postdocs. But if you have any questions in these days that I'm here, feel free to ask me. You can also contact these people. We are now fundraising to support the students and the postdocs to come. And CFNS is actually agreed to sponsor us. So I am here. You can catch me during coffee breaks or whatnot if you have any questions. So thank you.
Thank you.
You also have an evening session.
I'm curious about something. So you mentioned that you tune the quark masses in order to then understand what masses of the patterns, the mass of the point to some particular mass. So quark masses themselves, so we know that up and down quarks, they have geometry mass, and other quarks are more massive. So is lattice the best place where quark masses are known from themselves?
Well, for us, it's an input parameter. You basically, it's a very complicated conversation because, for instance, what I haven't mentioned is that the lattice spacing, you also have to tune. You have to, you don't know what it is until you measure a physical quantity and then you use an experimental value to compare it with that one. So I know I'm calculating, let's say, the physical parameters, and I calculate the omega mass, and then I compare the omega mass with what I calculate, and from that I can extract the information what the lattice spacing is. So I am very reluctant to say it's the best way to know that.
Other questions? Everybody's waiting for coffee break.
Yeah.
Coffee break for us. So let's thank Martha once again. If any of you wrap a small purse, Belroy, it's
There's my notes.
there. Okay, perfect. It's there. We didn't see it.
Appreciate it.
Excellent. All right, coffee break.
Sorry, yeah, yeah.
Sure.
So